Hello, a very good evening to all of you. So today we'll discuss about aromaticity and homoaromaticity, that is aromatic compound and homoaromatic compound. I have seen many students lack this concept. They can't exactly differentiate and they don't understand even this homoaromaticity. So I'll try to explain in very easy language so that you all can understand. So first start with aromaticity. Now what are aromatic compound actually? So just in a very easy language, if I say a compound to be aromatic, if a compound for a compound to be aromatic, it must satisfy these four conditions. If a compound satisfies these four conditions, then it is aromatic. First one is it must be cyclic. So I hope you all know what is cyclic and what is open chain, right? For example, this is open chain, right? There is no you start from here and you end here. It's not cyclic, but this is cyclic, right? So this is a cyclic. So the first condition is cyclic. The second condition is planar. The compound must be planar so that the conjugation is not disturbed or is not like it doesn't face any obstacle. The third option is what? First one is cyclic, second one is planar, third one is there must be by any means of conjugation. And I have already uploaded how many different types of conjugation are generally seen in a compound. So please check that video. And the third one is conjugation. And fourth one is Hakel's rule. Okay. Hakel's rule. Now what does this rule say? This is actually 4n plus 2 pi electrons where n can be 0, 1, 2, 3 and so on. When n 0, then 2 pi electron, and n 1, then 6 pi electron, like this and so on. So when these four conditions are satisfied, only then a compound becomes cyclic. Now you take this is benzene, right? This is cyclic, okay, first condition is satisfied. This is planar, all are sp2, all are planar. Conjugation, yes, sigma pi, sigma pi, sigma pi. Hakel's rule, see, there is n equals to 1, then 6 pi electron, 1, 2, 3, 4, 5, 6. 6 pi electrons are involved. So actually it look like this, 6 p orbitals are there. So this electron cloud, it's also above and below the plane. Okay, also above and also below the plane, right? Now let's come to the point homoaromaticity. Okay, before that I'll give another few examples of aromatic compound for your better understanding. You see this compound pyridine. This is called pyridine. Okay, this is also aromatic compound. See the pi electrons 1, 2, 3, 4, 5, 6. Just don't count this lone pair because this lone pair is not involved in conjugation. Now why so? If you draw the structure, you will see it's similar. The ring is similar like benzene. There are 6 pi electrons are delocalized above and below the plane. That's all right. But this lone pair, it is actually perpendicular to this benzene ring. Okay, so this does not take part in conjugation. So that's why we won't count this lone pair. So only 6 pi electron is involved. Okay, this is aromatic compound. If I take this one, pyrrole, this is also aromatic. Now you have to count this one because this is in conjugation. Okay, this is in conjugation. Okay, now see this is in conjugation. So you have to count 2 electrons here and 2 electrons here, 2 electrons here. So overall 6 pi electrons. This is aromatic compound. Correct. So these are some examples of aromatic compound just to give you a very basic idea about aromatic compound. Now let's come to the point of homoaromaticity. Now see, homoaromaticity is nothing but a special case of aromaticity. So homoaromaticity or homoaromatic compounds are what? They are special class of aromatic compound. Okay. Now, why special? Because here actually the conjugation is disrupted. Disrupted means there is an obstacle. Disrupted by one sp3 hybridized carbon. Means otherwise all carbon will be sp2 planar, but only there will be one sp3 hybridized carbon. For example, I am giving you an example. This is cyclooctatetraene. 4 double bonds are there. Let me know whether you know that this compound is aromatic or not. Okay, I'll upload a detailed video on that later. So when you treat this with acid, what will happen? This double bond will there will be electrophilic substitution, and it will look like this. One hydrogen is attached there and the positive charge. So see here, this is sp2 carbocation, this is sp2, 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 but this carbon, this is sp3, right? This is sp3. So otherwise it's a 1, 2, 3, 4, 5, 6. 6 pi electrons are involved. This is cyclic, everything is perfect. But because of this sp3 carbon, the planarity is disrupted. So what this compound, actually what does this compound do? The compound behaves smartly, you know. It behaves really smartly. It stays like this. Let me draw 3, 4, 5, 6, 7, 8. There is this positive charge delocalization among 1, 2, 3, 4, 5, 6, 7 carbon atoms. But this one, this sp3 carbon, it stays above the plane. Okay, it stays above the plane. Now, but this one, these 7 carbon atoms, they are in one plane and 6 pi electrons are involved. So, it actually possesses some aromaticity. It's not like completely it loses aromaticity. It possesses some aromaticity, but the aromaticity here, of course, homoaromatic compounds aromaticity is less than pure aromatic compound. Okay, but it possesses some kind of some aromaticity. Similarly, this is called cyclooctatetra trianyl cation, and also there is another compound. It will be like this when you treat cyclobutene, and similarly you treat this with acid, it will also form a compound like this. See, this one sp2, 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 but this one is sp3. See, it also like stays like this, and the positive charge is distributed over this 3 carbons. Only this sp3 hybridized carbon, it stays above the plane. Okay, so I hope this is clear to you. What is the basic difference between these two? And I'll upload a lot more example on this aromatic compound, and another also there is another class of category, anti-aromatic compound, non-aromatic compound. I'll upload later. So let me know if you have any query. Thank you. Bye bye. Take care.